That is to start talking about toroidal compactification of string theory. So before that, we have some cleaning up operations to do with the one-loop algorithms. The first thing is this. Okay. The first thing is this. It is the issue of once we have an omega insert into your partition function. Okay, once we have an omega inserted into your partition function, what kind of tori are we going to allow ourselves to solve? So, you remember that what omega does is reverse the direction of sigma. Okay? Now, once we've got an omega in the game then, okay, we only want to sum over those tori for which sigma reversal is a symmetrical. Okay? Now, I don't know if you remember when we were deriving the metric on moduli space of the torus. We had two different descriptions of the torus. One was that the metric was flat, but with this identification. Okay? And the second was that we had the metric which with rectangular, with standard identifications, but a strange, though constant, metric. Okay? Now from both these points of view, we can say that sigma reversals require the metric to be rectangular, the thing to be rectangular. From this point of view, if you reverse sigma, it changes the identification to be the other way around. Okay? From the point of view of the metric, where you take a standard identification, what we will have is a d sigma d tau term in the metric, and that will change time under a sigma reversal. Okay? So the shapes that we integrate over when we have the sigma projection are simply rectangular. Moreover, we've chosen one direction, namely sigma, to be special, because we impose the orientation. Sigma goes to minus sigma, but we don't impose tau goes to minus tau. So now we don't anymore have the symmetry of flip of the two sides. So when we are integrating over all inequivalent such projection tori, firstly there's no tau, there's only a t, and secondly the range of integration is t goes from 0 to infinity. Okay? As we had used in the previous class. Now, there is a way of slicing up this integral. Now, if you remember, what we did in the previous class was to take this reversed torus and viewed it with the closed string channel. Okay? And there is a diagrammatic way of doing that, of looking at that is sometimes useful, that I now will explain. Look, this torus, because we're doing the trace up to an identification by omega. Okay? The way one way of representing this structure is by this. So in a diagram in which an ordinary torus is represented by this. That is, it's a rectangle, but this side is identified with this side, and this side is identified with this side. This other surface that we're doing the integral over, which is the integral when you have the projection with omega, is represented by this. Because this side continues to be identified with this side is identified with this side after a reverse. Okay? Now that's great. But I'm going to give you another way of looking at the same guy. Okay, let's look at it. This diagram is the same thing as a colored chalk that we used. I've done nothing. I've just taken this and split it into two halves. This side is identified with this side, and this side is identified with this side. Clear enough? Now, I break this up into two bits. me just write that. This is just a stupid way of saying this, because if I identify this side with this side, that's the same as this side. So far it looks like I'm behaving like a mathematician, like I'm playing around for no particular reason. Okay, so now comes the point. Now I take this, I'm actually taking this and flipping it. So this is okay, let me do 2 steps in one, if you can imagine it. Take it, flip it, and then since this side is the same as this, we can go and put it underneath here. First, imagine the piece of paper. Pull it out, turn it out. Okay? So then what does, let me do it. So what does this become? And now I just turn around this piece of paper. So this is, this keeps going up, this keeps going up, this guy goes, sorry, this one goes 1. This guy goes this way, and this guy goes this way. Okay? Now, since this side is the same as this, I can just take this underneath here and put it down. So this is the same as do you see what we is this clear? Let me live. This is 1, this is 2, this is 3, this is 4, and this is 5. So in 5 steps, we've gone from this to this. Is that clear? So what I want to show, what I try to explain to you is that this identification of the torus, the orientation reversal identification of the torus, is the same thing as this. Now what have we achieved here? What we've achieved is that in time now, okay, in time now, we've got the standard identification. No reversal. But we've got something funny. What we've got something funny on the space side. Here, there was nothing funny in space. Space was just identified, except once you went in time, you had to do, you did the trace after an insertion of an omega. Now, in the limit where t goes to 0, in the limit where t goes to 0, this thing becomes very small. So that's the same thing as this thing becoming standard and the space guy becoming very large. So what does this become? It becomes this. Okay, so this is an ordinary torus, so this is identified with this. But what's happening here is that half of the spatial cycle is identified with its other half. So if we draw the spatial cycle, this spatial circle like this, what's happening is that antipodal points are being identified. Such an identification has a name, it's called cross-cap. Okay? So this diagram is often represented by a diagram of a cross-cap propagating and a cross-cap. So this cycle is simple. It's ordinary trace. Ordinary trace, or if you view it by slicing this way, it's just ordinary boundary conditions for the closed tube. But propagating between two cross-caps. The fact that, you might remember that when we looked at the partition function involving the orientation preservation, we got an eta of 2t. The fact that we got the 2t was simply the fact that this height has gone, this height which was t has gone to 2t. Okay? And the modular transformation takes us to the picture where the closed string is propagating in time from one cross-cap to another. Very similar to the modular transformation that took the open string partition function to the closed string propagating from one boundary state. Any particular boundary condition like this, gives rise to some state in propagation like this. That state by itself is some sort of, you may not want to call it, but it's some state. So this, again, just like the boundary state issue, is the overlap through propagation between two particular states of the closed string. What state? That's determined by these boundary conditions. And it can be written down explicitly, as some of you, those of you who have brought them, probably know very explicitly. Okay? So, this is the this Klein bottle. Okay, so the name for the one loop diagram with the orientation reversal is the Klein bottle. Okay? And it's often said that the Klein bottle is a diagram with two cross caps. And now you understand what that means. Well, is this clear? Well, it does. This, in this way of thinking, there's no boundary.
Yes.
So it's true, it's a manifold without a boundary. It's no. You just trace through here, this makes it look like there's a boundary.
Yeah.
But it isn't. There's, yeah.
You can't call crosscaps a boundary.
It's not really a boundary, it's some. Yeah. However, what is true is that it will give rise to some state propagating in this closed region. That's basically the point. Okay? So this gives you a pictorial explanation for the modular transformation that we did. They represented it as some state propagating between two things. And the 2 to the power 26 that we found was simply, it can simply be identified as the square of the 1-point function of this cross-cap state with the dilaton of the graviton. Okay? So just like the boundary state associated with the open string and a dilaton dipole, which in some normalization is 1, here this guy has a dilaton dipole, which in the same normalization is 2 to the power 13. So that 2 to the power 13 squared gives you the 2 to the power 26. Okay? Now, let us look at the same diagrams, it's a little more mental gymnastics, with open strings. Okay, so suppose we have an open string. Suppose we've got an open string. Here we've got really, these endpoints are distinguished because we've got the Dirichlet boundary condition, Neumann boundary conditions. Okay, so an ordinary open string can be represented as this. And let's put some where this guy is identified with this guy. And these two boundaries have no identifications. But any boundary where there's no arrow is going to be a boundary with Neumann boundary conditions. Okay? So this is our representation for an ordinary torus diagram, ordinary one-loop diagram for the open strings. That's clear? Now what we want to do is the same identification, but with the orientation reversal. So this is the fourth diagram. Remember we had some 4 diagrams. There was no orientation reversal for closed strings, no orientation reversal for closed strings, no orientation reversal for open strings like this, and the orientation reversal for open strings. So that's the last one we have to do. The orientation reversal for open strings is the one that gave you the 2 into 2 to the power 30. Okay, and I'm now going to give you a pictorial explanation for that. The fact that it gave you 2, that once we know that the Klein bottle, okay, gives you 2 into 10 to the power 26, and that the ordinary boundary, this boundary state gives you 1, then we should have expected this to be the case. So I'm going to up to sign which calculation it is. Okay, and the sign is of course very important. So let me try to explain this. So now we are interested now in the orientation, preserving value the orientation reverse. So that's this. Now once again I'm going to do this cheap trick of cutting it into 2. And here I can use white because this is this, sorry. This is this, it was this and that. So that's this and this. Correct? Okay. Now, if you permit me, I'll do many steps in one. First, I break this off as before. Okay, so let me just do that here. Change nothing. Then in my head, I flip and join. Okay, can you see? What am I getting? What I'm getting is twice the height, but what do we have? On this side, it was this and this. So just Neumann. On this side, it was this and this. So what do you get? Exactly. And what about here? Nothing. This is just ordinary identification. Okay? So do you see that what this diagram is from closed string exchange is if we represent Neumann boundary conditions by a cylinder with nothing and the cross cap by cross cap, that this is one Neumann and one cross cap. Okay? So we've seen that you see the dilaton dipole for the cross cap in units in which the dilaton dipole was 1. Yeah? The dilaton dipole for the cross cap was plus minus 2 to the 13. Why do I say plus minus? I say we can't plus minus because we cannot distinguish. Because had it been either plus or minus, the Klein bottle would have given us the same answer because it has the same thing square. Okay? So this is plus minus. So if you have this diagram, there are 2 ways of where to put this side or that side. That's the extra factor. 2. And so basically what should you expect with the number here? You should expect 2 into 2 to the power 13 with a plus minus. The point is that the sign happens to be minus. Okay? And now you understand the formula that we have. The formula which I've written as 1 but it's actually n squared. Because it's the Neumann. You see, Chan pattern factors live on the Neumann boundary condition. So there was n squared minus 2n 2 to the power 13. This n, how do you understand from this diagram? There's only one of these. N comes from summing over the Chan pattern factors from each of the Neumann boundary conditions. Okay, so from this point of view, this is 2n 13 plus 2 to the power 26.
Why did this factor n come to the center?
Why did this factor n come to the center? Well, it came from calculation, as we saw last time. And from here, because you see, it's an overlap between 2 sources. At one end, you have to trace over the Chan pattern factors. At the other end, there are no Chan. Okay? So the same reason we got the n squared. Because there were actually 2. Okay? So this way of thinking of it makes it diagrammatically clear that we're going to get a perfect square. You see, because what we're getting is either this going to either this okay, now so you get this plus 2 times cross plus this, which is the structure of a perfect square.
That minus had to be there, but
why did it have to be there? I mean, it is there. That was a calculation.
This will be cancelled. Yeah, how is it coming from calculation?
From calculation? How does it come from the calculation? Now, to actually get it from the calculation, the way you do it is actually perform the modular transformation of this thing. Okay, now this is something I wasn't planning to go through in class. Okay, but I'll tell you. This is the only place in this semester where we will actually need properties of theta functions. Okay, the point is that when we looked at the eta function, I told you that about 100 years ago, geometers have written down many nice functions. Okay, and then let me quickly just give you the basic definitions. Okay, let me quickly tell you the basic definitions, and then I'll tell you at least very briefly where that means. Good. Theta. 214 to 216. Okay. Alright. So the definitions that these people gave us 100 years ago were this: theta E AB. Right. So there's this thing that is defined as theta AB of nu and tau. Okay, so let me write it down. Okay, first, actually we don't need it. So let's say theta of nu and tau. Is defined as follows: some n is equal to minus infinity to infinity of exponential I pi n squared tau plus 2 pi I n Okay, this is the sum formula. Now there's also product formula. Product formula is theta of nu tau is equal to product m is equal to 1 to infinity 1 minus q to the power m of 1 plus z q to the power m minus 1. Sorry, this is anyway, let me write it down. 1 by z q to the power m minus half, where q is as e to the power I by I tau, and z is equal to e to the power 2 by I d. Okay, so one can show that this is the same as this. It's like expanding out, I presume. I've never really gone through this stuff very clearly. Anyway, it's kind of thing that really excites something. So, this object here is an infinite product. Okay. Now you see, suppose we didn't have these. That would be very closely related to the eta function. Up to q to the power minus 1 by 24. Now the main point of these theta functions is, and then there are then there are these generalizations of theta functions, which are called theta AB. So I'll try to go through them. Right? Theta AB of nu and tau, which is equal to exponential of pi I a square tau plus 2 pi I a nu b times theta of nu plus a tau plus b. Okay, given the theta function, in terms of it, you define this theta a. Now the main thing about these theta functions, the main really useful thing about these theta functions is that they have interesting modular transformation properties. For instance, theta 0, the things that will appear in many things that we do are theta 0, 0, theta 0, 1, theta 1, 0, and theta 1. No, these are all non-zero. But these are the things that will appear in our partition functions. Roughly speaking, when you have 0 or 1 is related to whether you have periodic boundary conditions around the side. Okay. And anyway, so there are many properties of these theta functions that are of interest, but properties that one can show just mathematically. For instance, theta 0, 0 is related to a modular transformation to theta 0, 0. Whereas theta 0, 1 is related to theta 1, 0. Theta 1, 0 is related, of course, to theta 0, 1, and theta 1, 1 is related to itself. Right, theta 1, 1. Okay.
So both the basis modular transformations take just this. There is no linear combination.
I was talking about the tau goes to 1 by tau. Okay. The other one's more trivial. No, the other one relates other things. But the one of interest is the tau goes to 1 minus 1 by tau. Now, why have I said all this? Okay. Why I said all this is that it's possible to write the unoriented open string partition function in terms of one of these theta functions. Okay. Let us, since we've gone through all this, let us understand what is that. So, let's remember what we had for the open string partition function. Okay. What we had for the open string partition function was 1 over q to the power 24. 1 over q to the power 24, and then we had 1 plus q into 1 minus q squared, and 1 plus q, blah blah blah. And this whole thing to the right power. And this whole thing to the power 24. Okay? So the question of interest is, can we take this infinite product and write it in terms of theta? And the answer is yes, Kolchinsky's done that. So let me write down the claim and then we check it. This is theta 0, 0 of 0 to I2. times theta of 2i. Okay, so this is the claim. The claim is that this infinite product can be written in terms of, okay, 0, 0 presumably is going nothing. Maybe no shifts. No shifts. So it's just this basic theta function. That it's this basic theta function of 2it times theta. Now let's see if we can check that. The product representation should be useful thing here. Let's see. 0, 0 and 2it. Wait, so now what are we? So firstly, this is 0. You see, firstly, q appears here, and we want things only in q squares. Okay, so let's just write down what this is, and then. So this guy here is product m is equal to 1 to infinity 1 minus q to the power m. Now z is just 1 plus q to the power m minus 1 1 plus q to the power m minus half by 2.
That was by z.
By z. Now, so now suppose I do theta 0, 0 of 2i. That's effectively 2m, it's just squaring q. 2m minus 2 and 2m minus 1. Okay. Now, what do we actually have? Okay. I'm clearing this. Sorry,
you shouldn't beat up some side. I mean, you got 2 out, I out. Now is IT.
No, q is e to the power
Okay.
at it. It's the same convention being used when writing down the partition function. Okay, so now let's write this out. So I'm going to write this times eta. Times eta, right? This actually he claimed was that this is square root of this. So this to the power 24 is this theta times eta to the power 12. This is claimed. Okay, times some 0 point energy density. Let me check that. So what this, and then I'll also write down eta, which is product m is equal to 1. So then I just put the extra factor 1 minus q to the power 2m. Okay, that is theta times eta. Okay, so now let's just write this out. What are the terms that we see? We see at n equals 1, we'll see 1 minus q square, and then that will be squared. But from n equals 1, we will also get this, which is 1 plus q. Right? And we will also get this, which is 1 at n equals 1. Okay, so from n equals 1, all of these terms just give us this. Now let's look at n equals 2. Okay, so n equals 2, from n equals to this term and this term give us 1 minus q squared, sorry, q to the 4 square. Okay, so that's this term and this term. You see what this term and this term are doing? Are taking into account the even oscillators, and the two of them, so that's why it's the square point. And the point is that this term taking account the odd oscillators. Okay? That's why the plus. And because when you do the product over all n, at each level you get 2 of them.
1 plus q raised to twice m minus 2, how can it take account of odd oscillators?
So yeah, you're right. I got that wrong. I think that's what it should be doing. I probably did. I'm sorry, both of them were. See, the difference between the two terms, the definition of the theta function was one came with a z and the other came with a 1 by z.
Yeah, but there was also q raised to q raised to m and q raised to m minus half.
No, both of them were m minus half. That was it. Let me just write down the definition. I'm sorry, I just copied it. It was 1 minus q to the power n, 1 plus z q to the power m minus half. Okay. 1 plus q to the power m minus half over z. That was the right. Okay, so these two terms are just the same. Okay, so these two terms are just so. Firstly, now we immediately see that it's perfect. And you immediately see that what it's doing is giving you the first two terms, one with the plus sign, one with the minus. Okay, so this quantity, okay, gives you exactly the module, the object that appears in the open string unoriented partition. Then you pick up a mathematics book and use the modular transformation property. Well, for eta we don't need a mathematics book, physics. But for theta you use the modular transformation property that the mathematicians use. Okay, since we've gone so far, I can tell you what that modular transformation property is. Okay, it is that when for nu is equal to 0, so we're only interested in this theta function at 0. That's even simple. So it's theta at 0 minus 1 by tau is equal to minus I tau to the power half exponential, but this is just 0, so in this case it's theta of okay, very similar modular transformation property to the eta function. You use that, plug in, okay, and that gives you exactly what that is. Yeah, I won't go through this exercise. Yes, some. It's very similar to what we've done, except that you have to use the modular transformation property also of the theta, not just theta. Okay. Great. So that's how you actually mathematically do the calculation. Okay. But all of that calculation was needed for as far as Kapkohl cancellation was concerned. Once we had this pictorial picture, was to get the sign right. Okay. Of course, that sign is very important to get right. You have to do that carefully. So you do it, you see that it's a minus. Okay. I think that's all I wanted to say about one loop diagrams. All I wanted to say about one loop partition function type diagrams in string theory. You see, in the last few lectures, the lectures where we've discussed these one loop diagrams, we have done basically no real calculation. In the sense that no numbers come out of what we did, except n is 2 to the power 13. Right? It's not like we got a final. It's very unlike the previous chapter, where at the end of the calculation we had this beautiful Venetiano. Okay? What can the interesting? Of course, it's possible to get one loop corrections to amplitudes, which will then give you explicit formulas. But those are not so interesting. Those are possible, and you can study them for detail. But at the level at which we're discussing this course, we're interested basically in the conceptual ideas. Okay? The conceptual ideas that we're getting, the study of these one-loop amplitudes here has given us lots of conceptual points that it's important to remember. And that will survive every time we compute a one-loop amplitude. That will have an explicit formula associated. Okay? What were the main points? Let's just recall that. Firstly, that it is always possible to view the boundaries of moduli space, so that the boundary of moduli space of your Riemann surface is the IR for some appropriate process. It could be that appropriate process didn't involve to open. It could be that you were thinking you were doing a one-loop open string diagram, and the boundary of moduli space is the IR for a process involving closed strings. That could be, but it's always possible, okay, to view the boundary of moduli space as some IR process. Okay. Therefore, all divergences in string theory can be related to some IR divergences. Some of these IR divergences are, a divergence is a divergence. If you have it, you don't get a finite number. So, some of these IR divergences are artifacts to do with the bosonic string, having their origin very firmly visible in the presence of closed string or open string bosonic tachyons. Those have no analog in the closed string. Other divergences are more serious because they have not to do with tachyons. We always knew that in the theory with tachyons we would end up with IR divergences. All of those we understand and we forget about. Right? The other divergences are more serious. They don't have anything to do with tachyons. The other divergences of the sort that we encountered are that we've got massless field, and that one-loop processes introduce sources for these fields. Okay? So that which destabilizes the vacuum. Those will have analogs in the superstring and can only be dealt with in perturbation theory if those sources can be arranged to cancel. Okay? And from this process, we were able to see two consistent closed string theories. The first one was just this closed string theory with no open strings. The only divergence in that guy was that associated with the tachyon. So the analogs for the superstring, meaning just closed string theory, which is the just type 2 or heterotic closed string theory, perfectly consistent with themselves. However, the other thing we could do is try to introduce open strings. The open strings had these boundary states which had sources, dilaton, dipoles. To cancel them, the only thing that we could do is to orientation reverse and fix the number of Chang-Patten factors in the open string. And that number was fixed to be 2 to the power 13 in the bosonic string, a number that becomes 2 to the power 5, which is SO32 in the superstring. That will be the process that gives rise to the superstring type 1 theory. Okay? So you've often heard that there are 5 classic superstring theories. Okay? There is the plain closed string theory. Turns out that because of fermions, there are 2 versions of that, called type 2a and type 2b theory. These are both analogs of just simple bosonic string with no funny stuff. Okay, then there is a funnier kind of closed string theory called the heterotic theory. The heterotic theory, as you will see as we go on in our studies, let me give you just 2 minutes, just so that you see where we're going. Let me just give you 2 minutes about what this closed string is. Just like we do bosonic string theory, starting with a bosonic action in the world sheet. The bosonic action is del x mu del x mu. We do superstring theory by starting on the world sheet with a supersymmetrized version of that action. So world sheet supersymmetrized version of that action. Del x plus psi bar del psi. Okay? The 2 type 2 strings are based on this world sheet. Okay. there's some issue about boundary conditions for these fermions, and the two type 2 strings differ in how we deal with these boundary conditions. We'll look at that in detail as well. Okay. Now, turns out that there is something else that is consistent to do. It's really weird, but it's consistent. And that is to put on the left moving side the superaction. Del x plus psi bar del psi. And to put on the right moving side the action for the bosonic string. Okay, I will have to explain this in detail. That will be next semester. Then we have to see that's all consistent. But it's consistent. That process gives rise to the heterotic string. And you know, the bosonic string lives in 26 dimensions. The superstring lives in 10 dimensions. We'll see that as we go. So this is a very funny thing where the left moving side lives in 26 dimensions. The right moving side lives in 10 dimensions. Now, the remaining 16 dimensions of the left moving side have to be compactified. And consistency tells you can't choose any old compactification. Consistency tells you that the compactification has to be that of the lattice associated with a lineage. And consistency tells you that it has to be a particular kind of lattice, self-dual lattice. Okay? And it turns out that there are only two gauge groups. The two such lattices in the world. First, the lattice associated with the gauge group SO32, the weight lattice, something related to the weight lattice by SO32. The second, the weight, something related to the weight lattice of E8 cross E3. This gives you the two heterotic strings. Okay? Lots of bells and whistles, but basically just closed string. However, there is the analog of what we just seen, which is closed strings and open strings. That's starting with one of the two type 2 theories. The one that allows you to do the orientation reversal operation. The one that treats both left moving and right moving fermions the same way. So it allows you to interchange. It's called type 2B theory. Okay. It's starting out with that theory and then introducing also open strings. In doing that, you're forced, in order to get rid of the del contact code, to allow with this orientation reversal map. That forces the gauge group, the number of pattern factors for the open string, to be 32, 2 to the 5, and that's type 1. So these are the five famous superstrings that you have all heard about in so much detail, and we will encounter them in much more detail next semester. But just to say that 4 of them are some souped up version of the closed bosonic string, and one of them is a souped up version of the open bosonic string. Okay? But you see now perhaps why Polchinski and me following Polchinski take this route of first trying to understand the bosonic string and then moving on. We see a lot of technical complexity just in our study of the bosonic string. But there are additional layers of technical complexity when we study the superstring, and it's nice to separate what you can do, nice to be able to go in steps. Also, the bosonic string forms half of the heterotic strings. We need to understand it. Okay, so end of spiel. Fine. Any other questions? Any questions or comments about one-loop diagrams? The lessons they hold for us. Actually, computing one-loop amplitudes in superstring theory is not too hard. Okay, it's not too hard, but it requires you to do the kind of thing we've done. Namely, to do modular integrals. Actually, we didn't even try to do the modular integrals. We just looked for diagrams. But to do the modular integrals with appropriate insertions. It's a pointless exercise trying to do them in the bosonic string, but because of the tachyon, we're always going to get infinity. Okay? But in the superstring, you can actually do that. There are no infinities. This cures the infinities of Einstein gravity. Okay, so maybe by the end of the next semester, we'll actually do a one-loop sketch. Okay, any other any questions or comments? Okay, about your assignments, people. I'm sorry, I keep slipping on this, but I promised today I'll send you a list of assignments. Okay, I promise I'll go through the problems, 0 and 20 problems. Okay, any questions or comments about this? Okay. So now we're going to move on to the study of toroidal compactifications of string theory, T-duality, and bosonic string, and to the study of D-primes. Okay, this is chapter 8 in Brzezinski. And this is the last of the chapters where there's also chapter 9, but chapter 9 is sort of an eclectic collection of topics. It's not the kind of chapter where you're supposed to, where it's systematic build-up. Chapter 8 is the last textbook-like chapter in our studies. We try to go through some of the topics in chapter 9 anyway, but if we complete chapter 8, I think we'll have done well in this course. Okay? So far, what we have been doing is studying string theory propagating in flat space. Okay? However, string theory, as we've seen, is a theory of gravity. So, computing little small scattering amplitudes in flat space is a little excursion of what gravity can do. Flat space is one of the solutions of Einstein gravity. And then you can compute a little small scattering amplitude. But all of us who study gravity know that there are plenty of interesting solutions of Einstein's theory of gravity. Okay? Or for instance, a black hole. I don't know. Lots of solutions of Einstein gravity. And one might want to do much more than study scattering in flat space. One might want to study the dynamics of Einstein gravity somehow. Okay? And a question you can ask is how what tools does string theory have to access? Now, to start with, we are quite limited because what we're doing is this first quantized approach, which has built in it the structure of S matrices. Okay? We're not starting from some Lagrangian for which we can find some new minimum, for instance. It's hard to put. You might think that it's hard to go far away from flat space and the kind of description that we're starting out with. However, string theory has a very interesting way of dealing with this issue. You see, all of the formalism that we built up, while explicitly built up for the particular case of string theory propagating in flat space, in the end, the structures that we encountered all make sense if we have any C equals 24 theory times the flat space theory on R1, 1. Why do we need the flat space theory on R1, 1? It is to be sure that we're getting a unitary theory. For instance, in our description of the no-ghost theorem, I don't know if you remember, but we took two directions, x25 and x26 especially. And we used them to get this n plus and n minus, and to show that the cohomology of the string was that of the line. But we use no other property of the closed of flat space theory. Of course, the net central charge has to add up to 26 in order to recover Y invariance. So if we just took the sigma model on R1, 1 times any C equals 24 unitary conformal theory. Okay? Everything that we've discussed in this course goes through without modification. Okay? The states that you can scatter are in one-to-one correspondence with the BRST cohomology of this theory. The BRST charge, it was built up entirely in terms of the stress tensor of the matter theory. So you just replace that stress tensor with the stress tensor of this theory, whatever it happens to be. Everything goes through without modification. The cohomology will be in one-to-one correspondence with the light code quantization. The cohomology is will be in one-to-one correspondence with primary operators of this matter theory, modulo operators that are both primary as well as descendants, and so on. All of that will go through without change. So, flat space is one background on which we can do string theory. But you can ask, are there other backgrounds on which we can do string theory? Now, the first way to address this question is, of course, take a small departure from flat space. Or take something that, in some sense, looks like flat space. And this is what Pranjal is going to tell us about the next class. Okay? Suppose you've got a sigma model. Suppose you've got a sigma model which is del alpha x mu, del alpha x mu g, which is a function of x. Remember, we've got 1 over 4 pi alpha prime. Now, provided this g mu nu is flat over distances that are large in string units, over large patches, we can always choose coordinates to make this look like flat space with small corrections. So, in some sense, such a sigma model is near to being flat space. Patch by patch is flat space, and then you have to patch these things together. Okay? So, such a sigma model should be near to the physics of flat space. So, Pranjal is going to ask the question, when is this? And then there is an extra thing you can add. You can also add such a Lagrangian term. A term that, if this was 0 or constant, would be, if this was 0, this constant would be a total derivative. Okay, because you can take this del alpha out. Yeah, but okay. So this is the kind. Both of these would be small corrections over flat space string theory, because over the patch region this is a constant and therefore it's total derivative, and therefore doesn't affect the physics. So both these Lagrangians over big patches describe just flat space propagation, strings propagating in flat space. But globally they describe more. Okay. So the question that Pranjal will ask for us next class is about the next sigma model like this. Okay? He will ask for us, when is this sigma model at the quantum level a conformal field? That was needed for the structure of string theory. We needed a C equals 24 conformal. Next, he will ask for us the question, what is the central charge of this thing? Okay? Now, the first question about when this guy is in conformal field is a question that we understand very well from how to answer from the techniques of quantum field theory. Because you see, from the point of view of quantum field theory, you should think of this as just the quantum field theory, but with an infinite number of coupling constants. Because the form of this g mu nu of x, different g mu nus of x give you different Lagrangians. And so every, for instance, term, the Taylor series expansion of g mu nu of x is a distinct coupling constant. Now you might think, wow, I'm not familiar with this. Why study scalar field theory in 4 dimensions? And I do field theory not like the condensed matter people want with the cutoff, but with no cutoff. I have only a few coupling constants because the attractive manifold of the renormalization group flows are small in number. I have a small, but that's not true in 2 dimensions. Why not? Because in 2 dimensions, naively x has dimension 0. So since x has dimension 0, x to the 20 is dimension 0. Naively. So you can put any function of x, and that continues to be classically marginal. So 2 dimensions, very special. Dimensional analysis tells you that a sigma model in 2 dimensions has an infinite number of marginal operators. Okay? And because of that, the space of possible theories in 2 dimensions is actually infinite. Now, so what Pranjal will do is to compute in some very clever way the beta function on the space of these couplings. Okay? By the way, just let's take 2 minutes off to few minutes off to understand the role of diffeomorphism invariance of the bulk from the point of the two-dimensional field theory. You see, suppose from the point of the two-dimensional field theory, x mu is just a field. Now, it's of course a fundamental fact of both classical as well as quantum physics that if you take an action and you make a field redefinition of the action, you recover the same physics. Okay? So, what is a diffeomorphism of the bulk? A diffeomorphism is that x prime is some function of x. Here, the bulk diffeomorphism is contained in the freedom to perform field redefinitions in this two dimension. Okay? And you can easily check, as I think Pranjal will for us, that under these field redefinitions of x's, the metric transforms in the way that a metric should. That in terms of new x primes, you get the same Lagrangian of the same form but just with the transform. Okay? So, the space of field theories in two dimensions is not labeled by G mu nu. It's labeled by G mu nu modulo field redefinitions, which then becomes G mu nu modulo diffeomorphisms. Okay? So it's exactly what you should expect from the bulk. This is beautifully interpreted. Okay. Then Pranjal will ask for us, what is the formula for the beta function? He'll do the calculation in one loop. Okay? And he will find that beta mu, that the beta function with, you can package an infinite number of beta functions into one formula. That you can look at how the whole function G mu nu runs as a function of scale. So beta mu nu, which is d G mu nu by d log lambda, and he will find, in the simplest case, let's say with B0, and nothing funny happening with the dilator, as he explained to us, that A is proportional to RB. When you turn on this B mu nu, there will be additional terms here, and there will also be a beta function for B mu. So, setting the beta function equal to 0 will give him some equations on these functions which are coupling constants of a two-dimensional. Okay? And what we will find is that these equations are precisely the equations that follow as equations of motion for a Lagrangian. Square root g e to the power minus 2 pi r plus 2 union. Okay? Just Einstein's action part into some matter. This h is d. Phi is the dilator. Okay, Pranjal will tell us some of this and I'll take over. Yeah. And moreover, this action is precisely the action whose classical physics reproduces the tree-level scattering, the low-energy tree-level scattering that we computed from Virasoro-Shapiro. Okay? So, what are we seeing? What we are seeing is that there is an action of string theory. That action of string theory can be used to compute classical scattering amplitudes by just expanding. We don't know what that action is. Okay, there's this attempt called closed string field theory, which in a very cumbersome way gives this action. It's not very useful. We don't know what that action is, but we have access to all its solutions. The solution, we don't really understand what the action is, but we understand the space of solutions to this action. And the space of solutions to this action is the set of 26 dimensional, C equals 26, two-dimensional conformal field theories. Okay? When we look at those conformal field theories, there are in some sense near to flat space. We see that it follows from a simple space-time effective action involving the fields of flat space, the metric and so on. Okay? However, we can go further and further away in the alpha prime expansion. See, Ranja's calculation will be done one loop in alpha prime. It is go to spaces that are curved very much in alpha prime units. There may not be a description like that for those theories. But all such theories give us good backgrounds. The logic for Pranjal's calculation will be that anything that he gets as a conformal field theory with the right central charge will be a good background of string theory. But we will abstract the principle away in general. Okay? So any conformal field theory, at least C equals 24 plus R of 1 and perhaps more. Conformal field theory on the worldsheet of the string will give us a good background of string theory. The fact that there are many different conformal field theories is simply from the point of view of the abstract structure of the Lagrangian of string theory, whatever that is, close to it. Field theory, maybe. So it's the fact that this Lagrangian has many solutions. No surprise. Einstein's Lagrangian has many solutions. Okay? And each of these solutions is a solution about which we can probe the theory in detail by computing scattering amplitudes using the ruler string. Okay? So this is the general structure of the theory that will emerge. Worldsheet techniques will allow us to access solutions of the theory without knowing what that theory is that we are accessing solutions of, in some sense. Without having a clean formulation of the Lagrangian itself. Okay? And it's one of the really beautiful facts about string theory, one which I believe Ashok was tightly involved in, but doesn't get full credit for. This connection between beta functions, equations of the worldsheet of the string, and Einstein's equation in spacetime, which is quite a miraculous connection if you think about it. Oh, what is the connection? The zeros of the beta function of the worldsheet of two-dimensional sigma model are solutions to Einstein's equations in spacetime. Wow. Anyone who sees that result can't help feeling there's something important going on. Yeah. This is one of the beautiful results of string theory that shows you how, our course has been very niggling so far. We've been in flat space, we've computed things about space matrices in great detail about flat space. But we know that there's this whole universe out there. There's a universe of solutions to Einstein's equations and more. And this is how string theory accesses this universe. Okay? Pranjal is going to explain much of it to us, and maybe it's too much to explain. Big assignment, I can help him. I can help him. He'll explain the technicalities and then we'll take over with some physics. Okay? So, this is the general structure of string theory, which I'm now going to feed into by studying toroidal compactification. But any questions or comments about this philosophical principle?
Then string theory cannot be defined on radius. Like you said, there was no mention of it can be arguably equal to some constant, right?
What?
You said it will be potential depend on R equal to 0, right?
Yeah, R mu equals 0. Actually, here you also get R mu plus some 8 stuff. Okay? But, what you will want, see, how does ADS come about as a solution? It comes about because of flux. Right? ADS is a solution, wouldn't be a solution without flux. Let's say ADS 5. It's a solution because we have 5-form flux. Right? So, we don't have these 5-form fluxes in the bosonic string, but you have the analog in terms of this HV. So, an ADS 3 type solution, you will be able to find it. But because of the HV.
ADS 3-form flux.
Exactly. Yeah.
For ADS is proportional to the G values.
Yeah. Basically, what you get is Mesomino.
Yes.
Yeah. So you have other solutions, only there's solutions of Einstein's equations. ADS is not a solution of Einstein's equation, but it is a solution of Einstein's equation with the cosmological constant. Cosmological constant comes from the flux. ADS it comes from a solution of pure type 2B theory. Type 2B theory doesn't have curve. Effective five-dimensional cosmological constant of the flux. Okay, good. Any other questions?
You mean this all the Python class and all those we equate on the S5, that will give you all this?
Exactly. I mean, what do we get if we do type 2B theory, this is type 2B theory, is we will get the beta function equations will be proportional to the equations of type 2B supergravity. And we know that ADS5 plus S5 is a solution of type 2B supergravity. Okay? Any other questions? Okay. So let's move away from generalities now and get to something specific. Let's look at toroidal compactification. So what's the basic idea? The basic idea is that we want to look at other solutions of string theory that are conformal field theories. Now, Pranjal in his lecture will try to build such solutions starting with flat space and making small variations. The problem with that is that while it's very beautiful, we can only do it perturbatively. You can only do it order by order in algebra. Because, one loop beta function, two loop beta function. Okay? You might ask before, in parallel to that investigation, can you find some other modified solutions of the theory that give you modified conformal field theories which are exact? Just exact conformal field theories exactly have the right central charge. Okay? Can we find such theories? And the answer, of course, is yes. Okay. Starting from the conformal field theory, there's del x with just one scalar field. It's easy to make 2 or 3 different kinds of daughter conformal field theory starting from this thing by doing some modding outs by symmetries. Okay? And in this, in the next 4 or 5 lectures, we will study 2 or 3 of these modding outs. The first modding out is simply x of sigma. Okay? Is identified with x of sigma plus 2 pi times constant. This gives you strings propagating not on flat space but on a circle of radius 2, of radius r. The second kind of Z symmetry is called an orbital. This will give you a conformal field theory on space will end at x equals 0. And we will also study the interplay between these two things. Identifications and translational identifications and such orbifolds. Okay. Now the great thing is that all my is starting with an exact conformal field theory, a very simple one, and modding out by things that are clearly symmetries of this theory. This is a symmetry because 2 minus signs give a plus sign. This is a symmetry because everything here, the action has a derivative. Okay? So it's very easy to construct the theories, and it's obvious that these theories are conformal. Nonetheless, the physical interpretation of what you get is very important. Because, for instance, physics on a circuit is very different from physics on a line. Okay? So, while these are very special examples, they're very interesting examples. Because, because circle compactifications are interesting. And B, because we can say things not approximately but exactly. Okay? So, the next 4 or 5 lectures will be devoted to the study of simple but exact compactifications of the boson string. Okay, philosophy clear?
So, for example, standard nonlinear sigma model story where suppose you had a U1 nonlinear sigma model, it has a linear sigma model limit, right, where it's a factorless circle doesn't matter. What would that be here?
No, I didn't understand. Say that again.
Suppose you had a U1 sigma model.
U1 sigma model, so just one direction.
Yeah. And generally we do have in lower energy limit, it looks like a linear sigma model, right? You can just take the small fluctuations and so on.
Yeah. So just del x.
Yeah. What is the correct with this story?
Yeah. So you can have del x with arbitrary compactification radius of x. let me say this again. What I will show you by the next 4 lectures is, for a while I stick to just studying with one x. So what we will do is to actually give you a complete classification of the space of C equals 1 conformal field theories. Okay? The space of C equals 1 conformal field theories will have a structure that looks something like this. There's one line corresponding to the radius of compactification, and another line corresponding to this overfold, and it's one of these miracles of 2D field theory that they meet somewhere. Overfold on a circle. I will explain all of this. Okay, this is an overfold with a circle. So the line is the radius of the circle. And we will find that an overfolded circle of a certain size is equal to a circle without overfolding of another size. And we will see this also. But you see, why I said this to you is the following. Universality, which is what you're appealing to by saying the low energy limit is something, tells you that you will reach some conformity. So it's very important to know what is the space of conformity. And the space of conformity theories has lines. So if you don't know anything about your U1 sigma model, you will end up somewhere. But you cannot say where. It's like Kostelis-Thouless. I don't know if you are familiar with it. Kostelis-Thouless thing. So the field is a phase. So it's like your U1. But the effective radius of that phase, in the sense, is a parameter. And once you go past a certain value of that parameter, you have a transition.
Yeah.
Okay? But you've got a whole line of conformal field theories. That's why you have phase transition. Okay? We're going to see all this in great detail. It's a beautiful thing in mathematical physics and makes contact with string compact. It's a beautiful thing. Okay, so let's start. So, we're first going to start with this study, with the study of this identification. It's the circle identification of the bosonic scalar field. Now, before we start studying it in string theory, just in field theory, there is just an ordinary Einstein gravity, ordinary space-time physics, circle compactification is already interesting. Okay? And I want to remind you of this fact. Okay? So the thing about it that's interesting is the Kaluza-Klein story. Okay? And I want to remind you of that. Okay. So suppose we've got some space, and one of our directions of space, let's call it x1, is x1 plus 2 pi. Okay. Now, you can ask, what is the most general set of metrics on a space of this form with a periodic identification like this, to start with, preserves translational invariance. A translational invariance in the x1 direction. Okay, we will soon loosen that requirement. But let me first ask this question. And the answer to this question is interesting. Okay, so let's call this 11. There are some non-compact directions, say 10 of them. It doesn't matter how many. Maybe I should call it 6. But some not. Okay. And okay. So now, see, you could put an arbitrary metric. You can put an arbitrary metric in the directions that don't involve this 11 object. Okay? And what you can do is to put Pulchinski calls this D. Okay? And you can put an arbitrary plus GBD times dxd dxd. But this is not all you can do. And that's the reason for the interest. You see, what you can do is also have cross terms between the dxd and the dxd. Okay? So the most general thing you can do is this. You can have dxd plus a mu dxd. Where all these fields are now functions only of the x direction. Square. Such a metric is clearly invariant under translations in the xd direction. Okay, more technically, it has an isometry. It has an isometry whose killing vector is just infinitesimal translations in xd. Yes?
You would understand the thing in the practice. The first thing is an index d is in contrast to the d1 d.
This one?
Yeah. But the second term does not have an index.
Because d is being treated as a special direction. You see, there's no mu index hanging around. So, dxd, so let's expand this. There's a term that's dxd dxd. There's a term that's a mu dxd. And there's a term that's a mu dx, mu dx, mu. These are all legitimate terms you can have in a metric. What you may be complaining about is that there's no symmetry between the mu direction and the d direction. But we're not demanding such a symmetry. We're explicitly going to break that. That's explicitly broken by the fact that xd is periodically identified. Well, the xd is not. Gone.
And as of now, you are treating GDD as a constant. It's not a function.
It could be a function of x mu. GDD, G mu, and A mu could be functions of x mu. So they're not functions of xd.
Not even a periodic. If it respects that periodicity.
I'm going to generalize soon, but at the moment, let's let them be just independent of everything. And look at fluctuations of this which will be allowed to respect that periodicity. But the background is just going to be treated. Okay? So what we're going to do is to study for 2 minutes such a background and see the role that A mu plays in such a background. That's the key thing. Okay, so firstly, what if we dimensionally reduce this theory on the circle, what fields do we get? We get a metric in the lower dimensional space. That's this thing. We get a scalar field. That's this thing. And clearly we have a vector field. That's it. The vector field is sort of like a massless vector field. Because everything in the whole game is massless. Okay? And we'll see this in great detail. Okay? So, a natural question is it a gauge boson? If so, associated with what group? And if it's a gauge boson associated with some group, where did that gauge symmetry come from? Since we didn't put it at the beginning, we started just with Einstein's actions. Einstein's equations. There's no gauge invariance. Coordinate invariance, no gauge invariance. Okay? So to answer this first question is very easy. You see, once we have restricted our attention to only those things that preserve translational invariance in the xd direction, okay, you can ask, what diffeomorphisms are we left with? So one kind of diffeomorphism is obviously this x mu. Diffeomorphisms in the remaining mu direction. That clearly respects, doesn't change anything. Okay, but there's something else one can make the coordinate change xd is equal to xd plus an arbitrary function of x. You see, this will not make anything depend on xd. Is that clear? It will not make anything depend on xd. But let's look at what effect it has on our metric. Okay, that's very easy to see. So this is the new quadrant, so let's call this tilde. Okay, so let me not mix these up. So let's just do xd is equal to xd tilde plus g of x mu, and x mu is equal to x mu tilde. Okay, so x mu tilde I won't bother with it. Okay, so let's look at this metric. So this metric here was g mu mu, bx mu, dx mu, plus gd dxd plus a mu dx. Now, I just substitute this in. Okay, these things were all functions of x mu's. Since x mu hasn't changed, inside the functions there's no change. The only place where there's any change at all is in the dxd. So in the dxd, I just substitute this in. So vxd is equal to dxd tilde. Okay, plus del mu g dx mu. Putting this into this, do you see that we get the same form of the metric in the x tilde coordinates? Once we make the identification, a tilde mu is equal to a mu plus d mu of g, which is just a simple U1 gauge transformation. So what we're seeing is this, that Einstein's equations on a circle, restricted to those configurations that preserve translation invariance of the circle, okay, has two kinds of diffeomorphisms. One is just diffeomorphisms in the dimensionally reduced space, and the second is a gauge transformation in the dimensionally reduced space. Okay?
So can any different compactification give non-abelian gauge?
Oh yeah, interesting question. So, for instance, a compactification of sphere gives non-abelian. Yes. So the answer is yes. These are called Freund-Rubin type compactifications. And the isometries. See, the isometries of the general rule is the isometries of the compactification space is a gauge group of the lower dimensional space. So here we just had U1 isometry. So we got a U1 gauge group. But if you have a more interesting isometry group, you get a more interesting gauge group. Okay? But we're studying just the simplest case. Okay. Great. Now, so the first lesson we got is the following. Gauge symmetry can come free out of gravity when we have compactification. This observation which was made by Kaluza and Klein 1920s, soon after Einstein's theory, really excited Einstein. And just a quick aside, but it really excited Einstein because Einstein always had held to the view that his equation R mu nu minus whatever had a beautiful side, which was the left hand side, and an ugly side, which was the right hand side. The beautiful side was beautiful because it's all geometry. The ugly side was for, some stress tensor for fluid or some particles. So the idea that perhaps the right hand side, that there's no right hand side, that all of the right hand side is effectively coming from the left hand side. Okay? That you will get, for instance, everything, at the time Einstein was doing his work, what are the fundamental instructions in you? Gravity and electromagnetism. Okay? So that you can get both gravity and electromagnetism, starting with just geometry. He found enormously exciting. And then he spent much of the rest of his life trying to find a geometrical description of the one element that was not there in Kaluza-Klein theory, namely charged matter. Because of course he knew there was charged matter. Contemporaries regarded his work as completely misguided. But I think string theorists now, looking back at what Einstein was doing, can quite appreciate it. Okay, that's just this. Okay, so what we're saying is that higher dimensional gravity gives rise to a lower dimensional diffeomorphism and lower dimensional general relativity with a residual gauge diffeomorphism. Okay, so it's not going to surprise you that when we work out the effective action for this, we take Einstein's Lagrangian, just plug in this form of the metric. One of the things we're going to get will be the Maxwell Lagrangian for helium. Why? Because it's not surprising at all, right? It's not surprising because we're going to get stuff that is two derivative, has to preserve gauge invariance. That's difficult. Unique choice for us. That is NVIDIA. So we're going to get that to be a scenario. Okay. The next question we're going to ask ourselves is, great, we've got gauge symmetry. What is the charge? How do we give charge under this gauge invariance? Is there a way of looking at fields that are charged under this gauge symmetry? Okay? And we're going to answer that question now. Okay. So to answer this question, we're going to look at, let us for a moment focus on G mu nu, A mu, and GDB, which are constants. That's a good thing to focus on because that then gives you a solution of Einstein's equations. Okay, so it's just constant, these obviously solved. Okay, for all values of these. Now, in such a background, I'm going to imagine that in addition to Einstein-Maxwell theory, in addition to the high dimensional Einstein theory, there was also a higher dimensional scalar field. I'm choosing a scalar field just for simplicity. Okay? So the Lagrangian of that scalar field was square root G mu nu d mu by d mu phi. Where that G mu nu and square root G is the full higher dimensional metric. Okay? And what I'm going to do now is to look at this action. I'm going to look at this action in dimensionally reduced terms. Okay? And what we will see, as you probably know, is that fields with n units of momentum around the circle will turn out to have charge n under this gauge symmetry. That's what I'm now going to try to show you. Alright. So all we need to do to show that is to evaluate this action. So what do we need to do? What do we need to evaluate in order to evaluate the action? We need to take G and invert it. And we need to find its determinant. Okay. So let's in order to so what's the structure of G? So the structure of G mu nu is this. We've got G mu nu. Okay. Then, according to our Lagrangian, we've got G d b A mu. Okay. G d b A mu. And we've got G d b A mu square. Sorry. This is just GBD. And here we have this is the structure of the metric, regarded as a matrix. Is that clear? Okay. So, in order to invert this metric, what we want to do is to invert this metric and also compute its determinant. Okay. And this, to start with, looks like a hard. Might to start with look like a hard algebraic problem. But let us, in order to figure out how to do this, let's retreat to the case where G mu nu, instead of being a matrix, was just one number. It was just one mu direction. Okay? And therefore A mu instead of a vector is also just one number. It's just one mu direction. Then, of course, the whole problem becomes 2 cross 2 and it's very easy to do. from getting the answer to the 2 cross 2 problem, it's very easy to guess the generalization. Okay, let's see how that goes. Okay, so let's take G mu nu, and this goes to some G. This is just one mu nu, and let's say A mu nu, A mu goes to A. Okay, so then our 2 cross 2 metric is what? This is G plus GDD A squared, GDD A, GDD A, and GDD. Okay? Now first the determinant. What's the determinant? Well, the determinant is G times GDD plus GDD squared, A squared, minus GDD squared, A squared. Okay? So this is just G times GDD. Okay? So what is the natural generalization of this to hide it if G was a full metric number? Square root G times GDD. Because G was just y squared, right? Yeah, it's because I want the generalization of square root G. Okay. Because that's what is going to go to this action. Okay. So good. So we've got up to a good start. We have square root G times G, square root G mu G times square root GDD. Okay? Times now whatever. Now the next thing we need to do is the inverse. This thing. Okay. So since this is 2 cross 2, that's not a big deal. Okay. Now once we know the determinant, all we need to do is to evaluate the minors and put it with the right minus signs. Okay, so now you guys will help me. So, oh, actually, there's this nice formula for 2 cross 2, right? Which is you interchange. Yeah. So, you help me if I'm getting it right. This is GDD, G plus GDD A squared. And then maybe minus of A, and then divide by the determinant.
Both minus that are both minus.
Both minus. Now let's just check if this is working. So this into this gives GDD into G and minus. Yeah, that looks good because that cancels this. This into this gives GDD squared A minus GDD squared A. It looks good, right? This into this gives now whatever the second row, first column minus GDD. Yeah, it looks good. Yeah, so it's looking good. Okay, so this is our inverse. Now what we want to do is to understand what this inverse is in the general case. Okay, so let's first write it out by multiplying through. So this is 1 over G, A over G, minus A over G, minus A over G, and 1 over G dd plus A squared by G. Now, who can give me a plausible generalization of this?
1 by G is less by G naught.
Excellent. So G mu nu. What's the plausible generalization of this? G mu nu in nu. No, 1 by G is inverse of G. Okay. Minus G mu nu in nu. Okay. And 1 over GDD is of course just 1 over GDD plus 1 over GDD. And what about this? A mu, G mu. Okay. So now we have the inverse. Now that we have the inverse, it's easy to write down the Lagrangian, our scalar field Lagrangian. So let's write it down. Okay. So we have this thing times G mu nu d mu phi d mu phi. That part is easy. Okay. Now let's look at these two terms. These two terms give us minus G mu nu A mu del mu phi, and the other guy was del d phi. Okay? And finally we get plus 1 by G dV del d phi the whole thing square. Okay. Minus A mu G mu nu. Was this GDD really there? I was gone. Something's changed.
And GDD plus.
Plus this. A mu this times del d phi squared. This is our full Lagrange. Okay, and this of course comes with factor of 2. But you see that this is the same thing, that this, and this combine together to give you G mu nu d mu phi plus A mu minus A mu. Oh, some signage. This was plus. Minus A mu del d phi, the whole thing squared, plus del d phi, the whole thing squared by whole thing times square root G times square root D. What does this tell you? This tells you A mu appears inside this covariant element. This becomes a covariant element. So what does it tell us? It tells us that what we should identify as charge for this gauge field is the d derivative of phi. So any field phi that maintains the isometry that our background prism is uncharged under this gauge field. But fields phi that carry momentum in this direction have charge. The momentum, of course, is quantized because the xd direction is periodic. So you can have 1, 2, 3, 4 units of momentum. Okay? So if you put that in, this will be of the form I n by Rv. So the charge is also quantized in units of 1 over RD. Of course, what the unit is, you can change by rescaling A later on. Okay? But what we have seen here is that not only do we get a gauge field, we also have particles that are charged under the gauge field. And charge under the gauge field is identified with momentum in the compactified direction. Is this clear?
And there is another term task mass. No, that is mass.
Which one? That's this?
Yes.
Yeah. Now this is going to be identified with the effective, as you said, effective mass of the particle. Okay? So suppose we start with the massless particle. Suppose we start with the massless particle in the higher dimensional space. Okay? If you've got momentum in this higher dimensional space, then higher and higher momentum objects have higher and higher mass. See, we don't, terms which have a mu are associated with charge. Terms which have this momentum but no a mu are just a quadratic term in the Lagrange. This just happens to be a fact that the same quantum number, namely the momentum in this direction, fixes both the mass and the charge of this particle.
So GD is like charge by mass.
What is charge by mass actually? Yeah, the fact that this GDD was here is of course very intuitive. Okay, why is it very intuitive? Because the effective mass of the particle should be set by the proper length. By the proper length of the circle. What is this effective mass turning out to be? There's a square root GDD and 1 over square root GD. So 1 over square root GD. The effective mass we would get here is 1 over r square. Yeah, sorry. The effective mass is the ratio between the kinetic term and distance. So we shouldn't take into account this GDD. So this one of this GDD by r square. Okay? Which is the proper size of that circle. Okay? So it's perfectly as you would expect. The fact that it's massive, of course, is because you have momentum. Okay? So what Kaluza-Klein reduction in this space of a scalar field, and this is qualitative, applies to every field, gives you particles that are increasingly high mass, but also increasingly high charge under this Kaluza-Klein region. Okay? Any questions or comments about this? Okay. Now the next thing we would like to do is to understand.
So essentially there's an infinite tower.
There's an infinite tower of lower dimensional fields with an infinite tower of masses, increasingly high masses, and an infinite tower of charges under the Kaluza. Is this clear? Okay, very simple algebra, very simple point, but very important physics, very important fact. Okay, now the next thing that we want to do is to do the same algebra, but for the much more involved situation of not starting with the massless scalar field, but the Einstein action itself. Okay, so what we want to do is to start with square root g or in higher dimension and go to the lower dimension. Now, can I leave this algebra as an exercise for you guys? Okay, will you actually do it when you get here? Okay, we'll put it on the assignment. Okay, so I'll leave this because it's just irritating algebra. That the thing that you would need to do, among other things, is, well, I'll leave it as an assignment. Okay, I'm just quoting the final answer. Final answer turns out to be pi r by kappa 0 d dx. Here, by the way, I'm assuming that none of the fields, all the fields have zero momentum in the translational invariant action. Okay, so we're looking at the dimensionally reduced action with no momentum in it. That's why the factor of r is common. d dx square root minus gd e to the power minus 2 phi d. I'll tell you what phi d is. Times rd minus 2 r. Actually, Kulchinsky actually starts with an e to the power minus. So, Einstein action with a diluter. Okay. Phi d and sigma is basically the GDP of the sort of factor. And GDP. Okay, so what we started out was a metric and a scalar field, a diluter. We end up with a metric, two scalar fields. The one we started with, and the one that we get from Kaluza-Klein reduction, and a gauge field. Okay, if you work with the original dilaton and sigma, you get mixing between the two. So you define a shifted field to remove the mixing. Okay. There's stuff we can discuss about this Lagrangian. Actually, there's interesting physics. For instance, it's sort of interesting to. It's here we've got this e to the power minus phi d factor outside Rd. It's interesting to go to the Einstein frame of this metric, and there are various interesting little exercises we could do. But we just leave this here. We just leave this for now and move on to string theory compact factors. Okay. Any questions or comments about Kaluza-Klein reduction, the basic physics. We've done two exercises. The first is to reduce the action for a charge scalar field, and that was so simple that we allowed it to have moment. The second is to reduce the action of Einstein action coupled to diluton. That was complicated, so we restrict our attention to things that didn't carry charge, and that's why we see nothing charged under this gauge field. The gauge field is just
What is A0?
A0 was the original Newton constant, D-dimensional, high dimensional.
Can you ask to the gauge field also if you have dependence on the direction?
Yes, you can. Okay, so if you take the gauge, no, I'm sorry. If you started with a higher dimensional gauge field, gauge field, then the Kaluza-Klein reduction of that would give mass and charge to that high dimension. But not to this, because this object is intrinsically a lower dimensional object. There is no sense in which A mu can pick up Kaluza-Klein. Okay? A mu is a gauge field in d-1 dimensions. There's no sense in which it was a gauge field in the original theory. Original high dimensional theory had only a metric. Is this clear? It's a good question.
If you start with the high dimensional gauge field,
Then you will get, of course. And the high dimensional, the modes, the momentum modes of the high gauge field will be charged under this Kaluza-Klein gauge field. Okay, fine. So in our introduction, let's move on to the study of string theory of atoms. So maybe we can do that. Let's do that. Okay, so next class what we'll actually, so we've got the background. Next class what we will do is actually study the string sigma model with periodic identifications. Understand how it works. Okay. Actually, Tuesday, though, Pranjal is going to be taking most of the next class. You're still on for Tuesday, Pranjal?
Can I do it on Thursday?
Sure, Thursday. So Tuesday we will continue our study. The stuff, Pranjal will continue.
So generally, do you consider the massless modes in this string theory? I also consider.
Why do we consider? Yeah, we often study the massless modes. Why is that the case? You see, because massless nodes are special for two reasons. The first reason is that massless nodes are always stable. Just because you cannot lower your mass by decaying if you're massless. All of the higher states of string theory, which are nice stable excitations in classical string theory, quantum mechanically, of course, decay. Okay? One of these guys, if it's sitting there, can decay into two massless guys. Okay, very much like some standard model. At this point, I should quote some classic standard model example. Unfortunately, I'll get it wrong. I'm not even sure I can distinguish between the 2-body and 3-body details. What? Like for instance, I was tempted to say very much like a mu1. But is it a mu1 decay 3-body? 3-body, right? So it's not very. Okay, I mean, there are contributions. Very much like something like pi. Okay, yeah. So, all of the heavy modes of string theory will not actually, in the quantum theory, will not stick around. Okay? So they're not real, they're unstable. Okay? That's the first reason. The second reason is, anyway, even if that weren't the case, if you're interested in physics, at energy scales that are small compared to 1 over square root alpha prime, the general philosophy of effective actions tells you that you should be able to get away with writing actions on even the massless. Exactly. Yeah. Let's see that. Yes.
So I think the then you get some chain reaction. You get some infighting system related. Then you compare on one more relations. It's whatever action we get is effective action we get in 4D. I think it contains the spectrum of massless.
Massless modes of that compactive. That's correct.
You start with 10, go to 5, and then you do one more.
Sir, what is the question? Are you making comment or question? I couldn't answer. Yeah.
Just for fun, we also add momentum modes to this compact.
Sure, you can.
What happens is it charged every time?
You will have charged massive spin to particles. From the lower dimensional point of view, they will not be gravitons. They will have effectively a mass.
Charge and mass
have to come together. Yeah. So you will have charged massive spin to particles. And you see, once something is massive, there are much fewer constraints on its dynamics than in its mass. Okay, excellent. Let's continue.